Welcome to the deep dive. Today we're looking at this incredible stack of astronomical research to try and answer one really mission-critical question.
Yeah, and it's a huge one.
Right. It's basically, how can scientists be absolutely certain about the existence of something that they have literally never seen, touched, or, fully understood?
It really is. I mean, it's one of the most profound puzzles in all of modern science. We're essentially exploring the ultimate invisible elephant in the room of our universe.
Completely. And I actually want to start by asking you, the listener, to do something kind of simple. Like, just take a look at your hand for a second. Really look at it. Notice the skin, the fingernails, those intricate little veins. And now I want you to think about the chair you're sitting in.
The walls of your room, too.
Exactly. The walls, the earth outside, the sun, even like every single star you have ever seen in the night sky.
Right.
Now, what if I told you that every single bit of that, like everything you've ever interacted with, touched, or detected in your entire life is essentially just the garnish?
It's wild to think about.
It is. Because it makes up only about, 1/6 of the actual matter in the universe? The other 5/6 is completely invisible.
Yeah, and it sounds impossible when you phrase it like that. I mean, it completely defies our everyday experience.
It really does.
Because we are so wired to believe that if something is real, we can see it, or at least, bump into it in the dark.
Okay, let's unpack this. Because we have this fascinating source material in front of us, and it keeps returning to this term, dark matter.
Right, dark matter.
But dark in a scientific context doesn't mean like a dark room, does it? I mean, it's not like it's casting a shadow.
No, far from it, actually. Dark is, well, it's a rather poor historical label that just kind of stuck.
Oh, really?
Yeah, it would be much more accurate if we called it invisible matter, or even, transparent matter.
Transparent matter.
Okay.
Because it gives off absolutely zero light. It absorbs zero light, and it reflects zero light.
If you were holding like a baseball-sized chunk of it in your palm right now, you wouldn't see it, and your fingers would pass right through it.
That's crazy.
It is utterly transparent, and yet the scientific community is overwhelmingly confident that it is there, heavily threading through every single galaxy, including our own Milky Way.
Which is just a wild concept to accept. I mean, how do you prove something is there when you can't see it, touch it, or even like bounce a radar beam off of it?
Well, by looking at what it does to the things we actually can see. The story of this discovery is really the ultimate masterclass in how science detects the invisible. We find it by mapping its effects. Basically, it leaves gravitational footprints.
Gravitational footprints, I like that.
Yeah.
Which brings us to the first massive footprint. Because to understand how we know this invisible stuff is there, we have to look at how things move.
Exactly.
And I want to start with our own solar system, just as a baseline for how gravity is supposed to work.
That is the perfect place to start. Because, to understand the invisible, we have to establish the rules for the visible.
Right.
So in our solar system, we have the sun sitting right in the center, and it holds all the planets in their orbits with its gravity.
Because almost all the mass of the solar system is concentrated right there in the middle, right?
Yes. And because of that, the gravitational pull gets weaker and weaker the further out you travel.
So think of it like standing next to a massive bonfire.
Oh, yeah, that's a good analogy.
When you're right up close, the heat is intense. But as you step back, the heat dissipates.
Exact.
And gravity works the exact same way. It follows an inverse square law, fading rapidly over distance.
That is a wonderful way to visualize it. And because gravity is the tether that keeps the planets whipping around in their orbits, the speed of those planetary orbits tells us exactly how strong the gravity is at that specific distance.
Oh, okay, that makes sense.
Right, so Mercury is practically skimming the sun's surface, comparatively speaking.
Yeah, it's super close.
So it has to whip around incredibly fast to avoid falling in. It completes an orbit in just 88 days.
Wow.
But if you travel way out to the icy edges of the solar system, out to Neptune, the gravitational tether from the sun is incredibly weak out there.
So Neptune is basically taking a leisurely stroll.
A very leisurely one. I mean, it takes Neptune 165 years to make a single trip around the sun.
That's a long year.
Right. But that falling off of speed with distance is the classic unbreakable signature of mass being concentrated in the center.
Okay, so if we take that exact same logic and we apply it to a whole galaxy, the setup looks pretty similar, doesn't it?
You would think so, yes.
Because when you look at a photograph of a classic spiral galaxy, it's this blindingly bright cluster of stars and glowing gas bunched up right in the middle.
Exactly.
And then it just kind of fades and thins out as you reach the edges. So naturally, you'd assume the outer stars at the edge of the galaxy should be moving slowly, just like Neptune.
Right. That was the unanimous assumption. It made perfect mathematical and intuitive sense to everyone, but science requires observation. So in the 1970s, an astronomer named Vera Rubin decided to actually measure those orbital speeds.
Wait, how do you even measure that? You can't exactly point a police radar gun at a star 50 million light years away and clock its speed.
Oh, no, you can't. But you use something very similar in principle, actually. It's called the Doppler effect, but with light instead of sound.
Oh, like when an ambulance goes by and the pitch changes?
Exactly like that, but visual. So as the galaxy spins, the stars on one side are moving toward us, and the stars on the other side are moving away.
Yeah.
When a star moves toward us, its light waves get compressed slightly, shifting toward the blue end of the spectrum.
And when it moves away.
The light stretches out, shifting toward the red end. So by measuring that tiny shift in color, Rubin could calculate exactly how fast the stars were moving.
That's brilliant.
It is. And what her measurements revealed completely broke the accepted rules of physics.
Let me guess. The outer stars weren't slowing down.
They weren't slowing down at all.
Wow.
The stars way out on the absolute fringes, where the visible glow of the galaxy basically fades to nothing.
Yeah.
They were orbiting just as fast as the stars, much closer to the dense center.
That is like finding out Neptune is racing around the sun at Mercury speed.
Exactly.
That shouldn't even be physically possible. I mean, the gravity from the glowing center of the galaxy shouldn't be anywhere near strong enough to hold on to those outer stars if they're moving that fast.
Right, they should literally be flung out into deep space, like a child spinning off a merry-go-round that's going too fast.
So why aren't they flying off?
Well, if we connect this to the bigger picture, the sheer physics of it leaves only one logical conclusion.
Okay.
If those outer stars are moving that wildly fast and they aren't flying off into the void, something invisible must be holding them in.
So there's extra gravity coming from somewhere.
Yes. There must be an absolutely massive amount of unseen matter forming a colossal halo around the galaxy, extending far, far beyond the glowing stars we can capture with telescopes.
And its gravitational grip is what's whipping those outer stars around.
Exactly. The galaxies were behaving as if they weighed far more than the sum of their visible parts.
Because there is an unseen anchor. Okay, that makes sense. Spinning galaxies are great, but if I'm a skeptic, I'm not rewriting the fundamental makeup of the universe based on just one spinning anomaly.
Sure.
Is there anything else out there proving this massive halo exists? Like, if there is this massive, heavy, invisible stuff everywhere, it has to affect something other than spinning stars, right?
Absolutely. You would want an independent line of evidence. And to find it, we have to look at how mass affects light itself.
Okay, now we're getting into the really mind-bending stuff.
Yeah, this requires bringing in Albert Einstein and his theory of general relativity. Einstein taught us that mass doesn't just act as an invisible tether. It actually bends the physical fabric of space. Like placing a heavy bowling ball in the middle of a trampoline. The fabric just sags around it.
Perfect analogy.
Yeah.
And light travels along that fabric. So if a beam of light from a distant object passes by something incredibly heavy, like a massive cluster of galaxies, it doesn't travel in a straight line.
Because the line isn't straight anymore.
Right. It follows the dip in the fabric. The heavy object bends the path of the light, acting just like a giant cosmic magnifying glass.
Or kind of like looking through the bottom of a thick wine glass. If you slide the base of a wine glass over a piece of text, the letters warp and stretch and distort.
That is exactly what astronomers see when they point their telescopes at massive clusters of galaxies, and we're talking hundreds of galaxies bound together by gravity here.
So a huge amount of mass.
Yes. They see the light from even more distant background galaxies getting stretched, smeared, and twisted into bizarre arcs and rings around the cluster.
Oh, wow.
And this phenomena is called gravitational lensing. Gravitational lensing. Okay, so what does this all mean? How does a visual smear of light in a telescope translate into a measurement of something's weight?
It basically comes down to the geometry of that bend. By measuring the exact curvature of those scratched light smears, physicists can calculate precisely how strong the lens is.
So they can kind of reverse engineer it?
Exactly. They mathematically reverse engineer the distortion to figure out exactly how much mass must be sitting there in the middle to bend the light by that specific amount.
And when they crunch those numbers,
Every single time, the cluster weighs 5, sometimes 6 times more than all the visible stars and glowing gas can account for.
that is wild.
The light is being heavily warped by something that simply isn't shining. The lensing literally weighs the invisible.
Okay, I have to jump in here and play devil's advocate for a second, because I know what you, the listener, are probably thinking as you listen to this.
Go for it.
We are throwing around concepts like invisible matter and exotic transparent halos. But why does it have to be exotic?
What do you mean?
Well, why couldn't this missing mass just be regular stuff sitting in the dark? Like, I don't know, dead stars that burned out long ago, rogue planets floating without a sun,
Right.
black holes.
Or just massive, dense clouds of cold gas.
Exactly. Stuff that's simply too dark for our telescopes to pick up.
It is a completely sensible, grounded objection. And honestly, it is the very first thing the scientific community assumed, too.
Really?
Oh, yeah. They even gave it an acronym, MACHOS, which stands for Massive Compact Halo Objects.
Machos, I love that.
It's a beautifully reasonable idea, and scientists rigorously tested it for years. But the evidence ultimately came back with a resounding no.
Why, though? If this matter is dark, how do we confidently know it's not just made of dark atoms?
What's fascinating here is that the answer doesn't come from looking at galaxies today, but from looking at the very beginning of everything, the Big Bang.
Okay, you've got my attention.
We actually understand the physics of the early universe incredibly well. The early universe was a cosmic furnace of unimaginable heat and pressure, and we can calculate the exact conditions of that furnace and figure out exactly how much ordinary matter, protons, neutrons, the building blocks that make up atoms, was forged in those first few minutes before things cooled down.
Hold on. How do we have a receipt for a cosmic furnace that burned out 14 billion years ago? How can we possibly verify that math?
By looking at the oldest light in the universe, it's called the cosmic microwave background.
Okay.
It is literally the afterglow of the Big Bang, still echoing through space right now. By studying the tiny temperature variations in that afterglow, and by measuring the exact ratio of the simplest elements in the universe, like how much hydrogen exists compared to how much helium, we can determine the exact density of the universe during those first few minutes.
Oh, wow. So it leaves a permanent signature.
It does. And that density tells us the absolute maximum amount of normal atomic matter the Big Bang was physically capable of producing.
So we literally have a cosmic inventory. And what happens when we compare that inventory to the total weight of the dark matter we've been measuring with those spinning galaxies and bending light?
The books simply do not balance.
Not enough atoms.
Not even close. If all the dark matter in the universe was just dead stars, cold gas, and rogue planets, regular atomic matter, we would need far more atoms than the Big Bang was physically capable of manufacturing.
Wow. So it's not just a matter of our telescopes being too weak to spot it. The math of the universe's birth proves it fundamentally cannot be made of the same atomic stuff as us.
Exactly. It is something entirely different, a totally new type of matter. It has mass, and therefore it has gravity, but it doesn't interact with electromagnetism at all.
Which means no light.
Right. It doesn't absorb or emit light, and it barely interacts with normal matter.
I really want you to pause and visualize this right now. Because this isn't just some abstract math problem floating out in deep space.
No, it's very local.
Right. Because dark matter is threaded through our entire galaxy to hold it together. And because it doesn't interact with regular atomic matter, it means this invisible substance is passing right through you in this exact moment.
It is.
It is passing through the room you're sitting in,
slipping
right through the spaces between the atoms in your body, and traveling through the entire planet Earth, and you don't feel a thing.
It is very much like a ghost, albeit a very heavy one.
A heavy ghost, I like that.
But because we can't touch it or, bottle it in a lab, there is one final, incredibly clever counter-argument that physicists had to wrestle with.
Oh, what's that?
Well, some scientists asked a really provocative question. What if the invisible matter isn't there at all? What if our understanding of the universe is just flawed?
Oh, that is an interesting pivot. Like maybe gravity doesn't fade away following that inverse square law over massive galactic distances.
Exactly. They hypothesized that maybe the fundamental law of gravity behaves differently on a sprawling galactic scale.
So gravity itself changes.
That was the idea. Perhaps that tweaked gravity is what's holding onto the outer stars and bending the light, basically faking the effect of extra mass. It is a very serious idea in physics.
But how do you test a tweak in the fundamental laws of gravity? I mean, you can't put a whole galaxy in a laboratory and run experiments on it.
You can't, but you can look for a natural cosmic laboratory. And the universe provided us with a spectacular one, an event known as the bullet cluster.
Here's where it gets really interesting. Because the bullet cluster isn't just a group of galaxies, is it? It is a snapshot of an incredibly violent collision.
It is two massive clusters of galaxies crashing straight into each other at millions of miles per hour.
So think of it like this. Imagine two massive crowds of people running full speed at each other.
Okay.
Most of the ordinary matter in these galaxy clusters isn't actually the stars. It's huge, diffuse clouds of hot gas filling the space between the stars.
Right. The gas is where most of the normal mass is.
So when these clusters collide, those gas clouds slam together. It's like the running crowds are all wearing heavy, bulky winter coats and carrying huge duffel bags.
That's a great visual.
Thanks. When they hit in the middle, they experience immense friction. They tangle up, drag, slow down, and pile into a massive traffic jam right at the center of the collision.
But the dark matter.
Right. What if half the people in those crowds were invisible ghosts? They don't have heavy coats. They don't experience friction.
So what happens to them?
The ghosts would just walk right through the massive pileup unimpeded and keep on running.
And that is precisely what the observations of the bullet cluster revealed.
Really?
Yes. The ordinary matter, the hot, glowing gas, which we can see using X-ray telescopes, slammed together, created immense friction, and got stuck in the middle.
Just like the crowds in winter coats.
Exactly. But when astronomers use gravitational lensing, that light-bending trick we discussed earlier, to map out where the actual mass was,
Mass had moved on.
the vast majority of the mass had sailed straight through the collision without slowing down at all. The invisible mass and the visible gas had physically separated from one another.
The ghosts walked right out the other side.
They did.
This is why it's the ultimate smoking gun. Because if there is no dark matter, and it's just the visible gas exerting a weird, tweaked form of gravity, then the center of the gravity should have stayed anchored perfectly to the visible gas piled up in the middle.
Exactly. It forces the conclusion. You cannot tweak the math of gravity to explain why the gravitational pull is physically separated from the stuff that's supposed to be generating it.
That makes total sense.
It proves the mass is a physical, independent entity that is separate from the glowing gas.
The evidence is staggering when you lay it all out like that.
Yeah.
I mean, we have the spinning outer stars of galaxies behaving terribly. We have massive clusters warping the fabric of space and bending light.
We have the cosmic receipt from the Big Bang proving it isn't made of normal atoms.
Right. And we have the bullet cluster showing the mass physically separating from normal matter in a collision. These are completely independent methods measuring entirely different phenomena across the universe, and they all point to the exact same truth.
The foundation of the universe is built on a substance we cannot see.
And yet, with all of that overwhelming, multi-layered proof, well, we still don't actually know what it is.
No, we don't.
That's the part that just humbles you. We are on this subterranean stakeout for a ghost, and we still don't have a mugshot.
It truly is the great frontier of modern physics right now.
Yeah.
We know how much of it there is, we know where it congregates, and we know exactly how it shapes the cosmos on a macro scale.
But on a micro scale.
If you ask a physicist what a single dark matter particle looks like, they have to shrug. The leading theory is that it's a brand new kind of fundamental particle, something completely outside our current standard model.
To clarify for the listener, the standard model is basically the physicist's periodic table of particles, right? It catalogs every tiny building block we know of.
Exactly. Quarks, electrons, neutrinos. Dark matter isn't on that table. It's an entirely undiscovered species of particle.
So how on earth do you catch a particle that is currently passing straight through the Earth without hitting anything?
Very, very patiently. Physicists have built these exquisitely sensitive detectors. They take vats of ultra-pure liquid, like xenon, and they bury them deep, deep underground, often in abandoned gold mines or beneath mountains.
Why do they have to go a mile underground? Why not just do it in a lab on the surface?
To use the Earth itself as a shield. The surface of our planet is constantly being bombarded by cosmic rays and background radiation.
Oh, so it's too noisy.
Way too noisy. If you put a sensitive detector on the surface, it would be blinded by the noise of normal particles. But down there in the dark, beneath millions of tons of rock, these detectors sit in absolute perfect silence.
Just waiting.
They are waiting for a lottery ticket event. They are waiting for the incredibly rare, statistically minuscule chance that a dark matter particle, instead of slipping cleanly through the vast empty space inside an atom, actually scores a direct hit.
And bumps into an atomic nucleus.
Yes, causing a tiny, tiny flash of light.
And we have been waiting for decades, decades of brilliant scientists sitting in these subterranean layers, watching the monitors for a single definitive bump in the night, and so far, silence.
It's true.
Which has to be intensely frustrating, but, I mean, there is also a profound romance to it, isn't there? This quiet, generations-long stakeout for the invisible foundation of the universe.
It is exactly how frontier science operates. The final answer isn't in yet. But I find this to be one of the most wonderful situations in all of human inquiry.
How so?
Because we aren't just making wild philosophical guesses. We have rock-solid, verifiable data telling us a massive truth about reality. It's not a fudge factor. It is an honest, precisely stated mystery just waiting for the right experiment to crack it wide open.
That's a great way to put it.
Somewhere out there, everywhere out there, is the dominant form of matter in our cosmos, and we've only ever felt its gravitational pull.
It is incredible to wrap your mind around. Just to summarize where we've been today. You look up at the stars, you look at your own hands, and you are seeing just a tiny, tiny fraction of reality.
A very small slice.
We know dark matter's out there because galaxies spin far too fast for their visible weight, because heavy clusters warp light too sharply, and because galaxy collisions leave the invisible mass running right out the other side.
The universe is predominantly constructed of something we have barely met.
Which leaves me with one final kind of wild thought to end on. I want you to mull this over.
Oh, this should be good.
If dark matter is 5 times more abundant than the ordinary matter that makes up you, me, the Earth, and the stars, and it is passing all around us right now, could there be complex structures to it?
That is the million-dollar question.
Right. We know it barely interacts with us. But over billions of years, interacting with its own gravity, could there be dark matter clumps? Could the universe be filled with entirely invisible dark matter planets, or even massive shadow galaxies intertwined right here with our own, completely oblivious to our existence, just as we are to theirs?
The math and the sheer depth of the mystery leave the door open to so many incredible, humbling possibilities. We have really only scratched the surface.
Something to think about the next time you look up at the seemingly empty spaces in the night sky. The dark isn't empty at all. Thanks for joining us on this deep dive. We'll catch you next time.